Thank you very much. This kind of introduction, as already mentioned. I will talk today with the mechanical and fractal mechanics investigations of unilateral fiber reinforced thermoplastic polymer tapes. Wait a moment, doesn't work. No, it doesn't work. The middle button, yes, I did press. Yes, now it's yes. The schedule is as follows. Of a short introduction, I go to how to process these UT tapes, about the metals and the morphology of these tapes, and then give some information about how to test using the fractal mechanics assessments from the experimental point of view. Otherwise, I give some information of the results and discuss the results, and finally, I'd like to conclude the talk. Yes, this UT tapes is not a really new task because it has been used with a thermoset matrix, maybe epoxies, for example, but now it's changing. Task is changing to be replaced this epoxy matrix to the thermoplastic matrix. This is due to increase the applicability and to make the processing much easier, and also especially the properties of the matrix have to be related to the properties of the injection molded parts as used. Here are two examples. One is a more futuric, futuric applications of bionic lightweight power presented on the Muga, the acquisition Bundesgartenschau in Heilbronn, Germany in 2019. They're using UT tapes and glass plates to make some pavilion. Of course, you can use this UT tapes also as a reinforcing element in concrete to make architectural structures. More common, more generally, is they use in injection molded parts as a reinforcing element or to strengthen in given directions and given parts of this injection molded part, for example, in an automotive industry. This is just in use. The door module carrier of the Ford Focus. If you have Ford Focus, you will find that. And here you're using UT tape set as a reinforcing structure inside of the thermoplastics part. They are not visible from the outside, they're inside. So you can create a structure, a component to save the glass fibers, not to have to make glass fibers inside, maybe useful. They use mostly a short glass fiber to make such injection molded part. No, you can strengthen in some directions. You have higher yield and moldus in some direction. The other have the high ductility of the pool plane as well. So you can combine these different properties in one part. Now going to processing. The processing is not too difficult, but the problem here is because you have a lot of processing parameters, they can be right. You have a lot of material, you have a lot of fibers, the transfers of fiber can be right. So it's not too easy to find the optimum of quality, of processing, and of the properties. Yes, you have here and the fibers, they will separated by this splitting unit, and then will be treated by a liquid polymer using this extruder. Then they will flat it, cool down, flat again, and then the winter they will then collect it for further use, maybe in the injection molded part as already mentioned. You have different types. You have some created here. You have 5 the black ones are the Kammermeyer reinforced. Here have this nice color, the nice bronze color, the basaltic fibers, also in use because we have a company in the middle, in the middle center of Germany, they produce this basaltic fiber in the higher amount. And here you have an example of glass fibers. Of course, you can also use different matrices. You can also use bio-based polymers and also bio-based fibers. Yes, first of all, I use the polypropylene with glass fibers, very common. Also, in our chief industry, the Lorenz was already optimized, and we're looking to if we can optimize properties and the structure is better, and then we increase the pull-off force, means the force here, the reduction of the opening mold. This means here to make, and then you increase the line speed and make it faster and more cost-saving. And you can also combine 2 different processing parameters, but this doesn't work well because this keeps to an oscillation of the process, and the process will unstable, and you have more matrix inside. The aim of the investigation is to minimize the matrix content, to have the highest stiffness as possible, and at the same time you have also the problem because otherwise you have also to optimize the toughness, because during the use you have to have the material be high, and also during the inlining in the injection molding, you have a machine. You have to be sure that your fiber will be stable and not broke in parts. So this will be also to have also optimize the toughness as well. The other example is polymer 6 with carbon fibers, and here we carbon fibers are using neck fibers, so you have to using this plasma treatment to increase the surface energy of the carbon fibers, make it more useful to increase the interfiltration strains between the carbon fibers and the matrix, and using different pressure glass types of flow rates as well to find something that something is the same here as well as here. So you have as you the process partner have your particle variety, but cannot go in detail due to the reasons of time. So we're looking at the morphology. Yes, usually the fibers are well separated. They are colored because to make visible with a blue color from the outside. Otherwise, they are more or less invisible in this microscopic picture. Sometimes, and we have some layer. Sometimes this is a regional matrix, but not. And we measure the roughness here in that way, not this way, of course. And the roughness will be measured here as a 3D surface scan using a profilometer. And the roughness, why you measure the roughness? Because I expect that the fractal toughness, the crack propagation resistance in fiber direction is also related to the fractal toughness because of the underlying similar physical reasons. You can see that there are such value in set value in fiber direction has a variation of factor 3. These values are mostly related to the microstructure, so to the size of the glass fibers or the diameter of glass fibers. These are constant, so they have no influence. The same as carbon fibers. They are much smaller because the diameter of carbon fibers is smaller, of course, 5 compared to 10 microns. Here have no influence, more or less. Here you find a factor of 3 influence. This can be used maybe as a quality assessment to make and to analyze the fractal toughness in line, not using this complicated fractal mechanics approach, which is not useful for industrial approaches. Now I go to the fractal mechanics assessment. Yes, this examples in cost of fiber direction. We're using a multiple specimen approach. Where we have the same specimens, but we vary the ligament length. That means we have double notch edge tangent specimen. We have different crack lengths on both sides. This works well, but in fiber direction they are much more difficult to produce. So we have to have a single fiber. A single specimen approach. Clearly, we repeat it 20 times more, and using the single notch tangent specimens, and we have only one crack. Yes, with the same length. Maybe this is the half of the width of the specimen. Now we can look generally the Buchheim can be used, of course, in the cost of fiber direction, and because you can use also called post-gel fractal mechanics. It's not really yield, but we have to stick split behavior, and this can be interpreted as pseudoductile behavior. So we can use all this as a work of fracture approach. It's very easy to handle. We have to measure the crack length because the stable crack probe, because there is no stable crack, but we have to measure that. The single measure gives you is based on the linear fractures as well. We have the different integrated values cost of fiber direction and the J and the K value in fiber direction. Now I come to the results. Of course, it's not very nice. It's totally broken, but yeah. It's not as much before. You can generally have a lot of lines on this. They look very similar to this one. As you can see, that the close displacement diagrams are that similar. We have some slick process due to the fire pole alt and the breakage of the fibers, and then due to the self-similar process, we can use the approach of work fracture too. If we're plotting the work of fracture as a geometrized using the Buchheim method, we have a lot of scatter. This is to the stochastic process of crack propagation, typical of that such type of fiber, but you can measure the J value as well, and from the slope, and you have some you can distinguish between different materials and processing parameters, so it's possible to do that. Now we look into the results. Clearly, Buff's bullet placement approach gives the same value. Buff's from the qualitatively and the quantitative point of view, you have some influence of the processing parameter. Of course, you have also a clear difference in the fiber direction means the interfacial strength is differently influenced, and here you have a higher value, but here you have your cohesive path, because the crack goes not to the surface of the crack of the fiber matrix surface, but in the matrix. So you have a much higher values, but it's out of the scope of the investigation, so it's not of interest. Next, the same is more or less fine for the polyamide 6 fibers. It's always the same results. You have some outliner here. Maybe this is due to the same process, because you have only a very unstable processing, so we have a high value and you have the same recursive fracture, but it's not the same. We have lower matrix or higher matrix content inside, and therefore lower stiffness. The modulus is lower, so it's also out of our interest. And now some correlations. Generally, one can expect that the increase in the fiber, the J value fiber, that is a measure of the fiber matrix adhesion, can be also increase the fiber direction. Because fiber is this case, but I have not scatter. This is outside, but the reference was the best. So all other changes of the further changes of the processing model gives better the results. No, here have not a lot of changes from the first point of view, but looking to the reference, we'll see that the values, all our values in and across the fiber directions are higher. So the reference, the influence of the matrix, the fiber properties using this plum treatment gives better results. Next of all, why is this the case? Yes, for the untreated fibers, you have the fiber goes across to the fiber surface. Here you have sometimes a fiber matrix layer, because sometimes this is close to the crack, but not always directly to the surface of a crack. So some of the matrix is attached as a thin surface layer. This gives a reasonably higher toughness. Now we have to look for why we can use or develop a quality assessment program to avoid fracture mechanics investigation in the further views. How to increase how to increase the properties and how to measure the properties during inline. And inline can be measured. The thickness, of course, the roughness can be measured. Maybe also other things can be measured. I think the roughness value was I showed that the roughness value has the same idea or the same underlying physical meaning than the fracture task, because this is related to the interfacial strength between the fiber and the matrix. So that gives a clear correlation. That is nice. Here you have also a correlation not so pronounced, but you can see if you have maybe a higher roughness of say 15, you have good results. If you have higher roughness of say 80 or lower roughness and about 100 or 150, you have good results. You can measure the roughness and you can analyze the fracture toughness in the inline. So find a way to measure that inline. Now what I showed was that the unilateral fiber polymer tapes based on thermoplastic polymers and endless fibers are just produced in high quality. The fracture mechanical assessment of toughness of such UT tapes gives reasonable results. A lot of scatter, of course, but it's typical for the process of this, to the processing and due to the stochastic process of crack propagation. And the fracture toughness of UT tapes in cross or fiber directions is highly affected by the processing condition, but also by the fiber treatment. And the toughness of fiber direction is a measure of the matrix fiber adhesion influence the fiber fracture across to the fiber direction. This is due to the stick-grip process, easy to understand. And the last, I think that's the best and most important outcome of this research, that the surface roughness can be easily used as a quality assessment during the processing because of this correlation to matrix fiber and adhesion in process. That means in line during the processing of the UT tapes. Now I give my thanks to the funders of the work, and I thank you very much for your interest. And I think a lot of people are there. Thank you a lot to be here.